SwayamPrabha. Digital India. Educated India.
So, we will continue from where we left off in the last class. Basically, in the last class I defined streamlines and the stream function. The stream function is constant on the streamline, okay, and on the streamline the velocity is tangential to the streamline. Those are two things you have to remember. And the other thing we found is that if you have two streamlines, there is a constant value on each streamline. The difference in the constant values represents the flow rate. Okay. So, that is basically in nutshell what we did in the last class. Okay. So, streamlines are such that at each point the velocity is tangential to it. Okay, that is one thing. The stream function is a constant on the streamline, and between two streamlines the flow rate per unit depth is given by the delta psi value, the difference in the stream function values. Okay. And the other thing is the psi is defined only for 2D flows. Okay. And the other point which is possibly something which is obvious is two streamlines cannot intersect, because the intersect, that means the two tangents, okay, and the velocity at each point is uniquely defined. The velocity can't go in two different directions, okay, because if they intersect, the velocity can be tangential to only one of them, okay, one of the streamlines. So, that is basically in a nutshell what we saw in the last class. So, these are basically imaginary lines which you have, tangent to each line is in the same direction as the velocity vector, okay, and because it is the same line, you can think of these streamlines as if they are walls, because the liquid cannot penetrate, there is no normal component of velocity, velocity component only in the tangential direction. So, you can think of these streamlines as hypothetical tubes between which the liquid is flowing, okay. And the other thing of course is the stream function automatically satisfies the equation of continuity. I mean because that is the mass balance, okay. So, I have illustrated this for in Cartesian coordinates. You can do the same thing in cylindrical coordinates. All these properties have to hold, okay. In cylindrical coordinates, the way you define the stream function should be such that the equation of continuity should be satisfied. Same thing for spherical coordinates, okay. 2D flows, everything is just going to translate once you understand the physical concept. Only the math, some derivative may be coming in, okay. So, now we want to see how we can actually find solve problems for in 2D flows, find the velocity field. And before we go to that, I want to introduce one more concept, and that is called the concept of vorticity. Okay. I am going to use this symbol for omega because to make sure that otherwise this is the capital omega. The small omega and W look the same. So, to avoid that confusion, I am using capital omega for vorticity, okay. So, the way this omega is defined, omega is defined as curl of V vector, del cross V, that is the definition of omega, okay. And you all know how to calculate the cross product. So, we will do exactly that. We will write this as, this is going to be a vector, right, I j k d by dx, d by dy, d by dz and u v w or ux vx, vx vy vz, whatever. This is how you would calculate the curl, okay. I mean A cross B, this is what you do. So, A is del operator, velocity is this. You calculate this thing, and remember we are looking at 2-dimensional flows right now, okay. So, for 2D flows of any flow for that matter, what is this going to be equal to? I multiplied by dw by dy minus d by dz of V, right. That is the cross product. I mean just evaluating the matrix, minus j times what is it, dw by dx minus du by dz plus k times dv by dx minus du by dy. Since we are looking mainly at 2D flows, okay, so basically in the z direction there is going to be no variation, okay. So, this V with respect to z is going to go to 0 and W is also 0 because again only components are u and v varying in x and y, okay. So, for 2D flows u and v are functions of x and y alone and w and d by dz are 0, okay. So, what this means is these guys do not contribute, no variation in z, w 0, so all those guys go off. Only thing remaining is this third term. So, curl of V, which is omega, is going to be given by k times dv by dx minus du by dy, okay. Now, I want to write the v and the u in terms of the stream functions which we defined in the last class, okay. So, how is v and u defined? So, v was defined as minus d psi by dx and u as d psi by dy, okay. So, just substitute that here, minus d psi by dx. So basically omega turns out to be is a vector, and it turns out to be d square psi by, substitute for v, d minus d by dx, right, minus d square psi by dx squared minus d square psi by dy squared, and this is minus k del square psi. Okay. So basically this is the relationship between the vorticity and the stream function. So if I tell you what the stream function is, you can find the vorticity. Now there is a class of flows which are called irrotational flows. Okay. So if irrotational flows irrotational flows are flows for which the vorticity is 0. Okay. Here omega equals 0. So basically omega equal to 0 implies curl of V is 0. Now if you remember your mathematics, if the curl of something is 0, then you can write that particular quantity as a gradient of a scalar. Okay. So for the special class of irrotational flows, curl of V is 0, I can write V as the gradient of a scalar function. Okay. So this implies V can be written as gradient of phi. This is what is called a scalar potential. Okay. Why is this possible? Because if curl is 0 of something, that means I can write that as the gradient, but curl of grad is always 0. You can evaluate this, you can look at curl of grad using the definition of del cross del phi, you will see it automatically becomes 0. Okay. So this is something you can do. So all you have to do is ijk curl and put d phi dx, d phi dy, d phi dz and calculate, you will see that it becomes 0. Okay. So this is from your mathematics, or if it is not from your mathematics, you can verify it. It's a 1 minute thing and therefore you can do it. Okay. So basically what I am trying to tell you is that normally in general you cannot write V as gradient of a potential, but if the flow is irrotational, if omega is 0, I can write V as gradient of phi, which means Vx or u is d phi by dx, V is equal to d phi by dy, and w is d phi by dz. So when I am talking about irrotational flows, I am talking about things in terms of potential. I am not restricting myself to 2D. Potential, this kind of flow can also be done for 3D. Okay. Streamlines are defined only for 2D. Potential functions can be also be valid for 3D. Now there is some confusion which people have. Sometimes the people use inviscid when the viscosity is 0, irrotational, all interchangeably. Okay, but you have to be careful. Just because it is inviscid does not mean it is irrotational. So irrotational is defined as curl of V equal to 0. That is the only definition. If it turns out viscosity is 0 and for a particular flow field where viscosity is 0, if curl of V is 0, then you can call it irrotational. Not all inviscid flows are irrotational, number 1. Normally this inviscid approximation or this irrotational approximation is valid for when you are far away from walls, okay, because there the viscous effects do not show up. So for example, if you have a flat plate and you have a flow of a liquid over a flat plate, near the wall you have the boundary layer, but away from the boundary layer the flow is going to be uniform, there is no viscous effects, and you can calculate for a uniform flow field, curl of V will be 0, that flow is irrotational. Okay. So that is the whole point. So basically the point is, away from walls flow is irrotational. This is normally a reasonably good assumption. Okay. So let us look at this irrotational flow again. For irrotational flow, I said U is can be written as graph. Now some books may write the velocity vector as minus of grad phi. That is just a sign convention, because they want to be consistent with things like heat transfer, where you say Q equal to minus K del T, mass transfer, we say flux is minus D del C. So this also flow velocity is minus del V. So I mean, it's just something like a sign convention you can think of. Okay, so you don't have to be worried, but you can't keep changing. If you are saying V is grad phi at one point, you have to be consistent throughout. Somewhere in the middle, you can't start using a different sign convention. Okay. So anyway, so point is, some books may have a different sign convention, and sometimes a minus sign may come, because I am assuming that all of you are very sincere students, will be reading 5-6 books. So maybe you will get confused when you see different sign conventions. So anyway, if V is grad phi, equation of continuity has to be satisfied. Implies divergence of the V vector is 0, divergence of gradient of phi equal to 0, or del square phi must be 0. Okay. So before we proceed further, I just want to make one point and then we can proceed. So when I am trying to solve a fluid flow problem, all I have to do is I have to find my potential, assuming my flow is irrotational. Okay, I have to find the potential which will satisfy this boundary, this equation. Of course, the differential equation has to be subject to boundary conditions. I will satisfy subject to boundary conditions. I can find phi. Once I find phi, I can find u and v, the velocity components, because u is grad phi, and then put it in my Navier-Stokes equation, find pressure. Okay. For irrotational flows, life looks very simple, right? There is only one thing. So at a wall, what boundary condition must be satisfied? At the wall, we say, let us say wall is y equal to 0. Okay, you say u is 0 and v is 0. One is the no slip boundary condition, and the other no penetration boundary condition. Okay. So this implies u is d phi by dx equal to 0, and this implies d phi by dy equal to 0. Correct? Now when you have flow, I mean this is a boundary condition on u, this is a boundary condition on v, which as far as let me explain okay, supposing there is flow between two walls, and let us say at the other wall, at wall y equals 1, flow between two walls. Okay, I have again d phi by dx equal to 0 and d phi by dy equal to 0. Okay. So I have two walls, liquid is flowing through two walls, and this is what I am going to be solving. Okay, I am interested in the flow. I satisfy the no slip and the no penetration condition in both the walls. So now the problem is, I have 4 conditions, but what I have is only a second order equation. There are 2 conditions extra. Okay, so I am over specifying. When I solve my differential equation, I can need 2 constants, but I have 4 boundary conditions to satisfy. So I need to let go of 2 of the conditions. Okay, so which are the conditions I am going to let go of? I am going to recognize the fact that we have a situation where flow is irrotational, and I said something similar to inviscid, viscosity is not there. So, I am going to let go of the no slip condition and I am going to keep only the no penetration condition. Okay. So, this is the reason why I said when you have flow past a flat plate far away from the wall, I mean you do not have to satisfy boundary conditions. Okay. Near the wall only you have to satisfy the boundary conditions. So, when you are far away from the wall, you will only satisfy the no penetration condition, you do not satisfy the no slip condition. Okay. So, this is a singularity, okay, and I will explain what this when I do not have the irrotational flow assumption, this singularity will not be there. Okay. So, you have to understand mathematically the fact that this flow is inviscid is valid only far away from the wall, and therefore, one of the boundary conditions is let off. Okay. And the boundary condition which has to be let off is the one which is the no slip condition, not the no penetration condition. Okay. So, we have 4 boundary conditions, but second order differential equation. So, we let go of 2 boundary conditions. Which ones? The no slip conditions are not imposed. Okay. Because here irrotational is I do not want to say equal to, is similar to inviscid flow. So, for example, in reaction engineering you have plug flow reactor. In the plug flow reactor we say that the velocity profile is uniform across the cross section. Okay. There the no slip condition is not satisfied. That is an example of an irrotational flow. When the velocity is uniform across the cross section, when do you have uniform velocity? When there are no viscous effects. Okay. The liquid is slipping past the wall, the no slip condition is not satisfied. Okay. So, like a PFR you have, so see in a plug flow reactor, velocity is uniform across the cross section. So, the no slip condition is not satisfied, because if you satisfy the no slip condition, velocity has to be 0 and then you get some parabolic profile. Okay. And that is not an irrotational flow. So, anyway, so I want you to sit down and think about these different aspects, the mathematical perspective, the physical perspective, and try to understand why we are letting go of the no slip condition. Okay. So, okay. So, now so when we solve del square phi equal to 0, we impose only the del phi dot n equal to 0 as the boundary condition on a rigid wall. That is only the normal component of del phi dot n is the normal component of velocity. Okay. So, only that is imposed. I do not impose conditions on the tangential component. Okay. N dot del phi is okay. So, that is basically what it is. So, in some sense the flow field that you are going to get does not satisfy everything, does not satisfy the all the boundary conditions. Okay. So, some approximation has been made. So, this is going to be valid away from the solid wall, that is what it means, slightly away. Now, so this is whatever I have discussed is the special class of irrotational flows. Now, we are going to do the general problem when the flow is not irrotational. When the flow is rotational or general. Okay. So, of course, then the Navier-Stokes equations have to be satisfied. So, I am going to write the Navier-Stokes equation, okay, rho times du by dt plus u du by dx plus v du by dy equals minus dp by dx plus mu times d square u by dx squared plus d square u by dy squared. Okay. That is the x component, and now I write the y component. Okay. So, what is the thing? I said we are not interested in doing the thing in the primitive variables u and v. I want to convert things to stream function. Okay. So, I am going to write everything in terms of stream function, number 1. Number 2, I am going to eliminate the pressure by differentiating this with respect to y and differentiate this with respect to x and subtract. Okay. So, I need to start putting equation numbers 1 and 2, differentiate 1 with respect to y, 2 with respect to x, and I will do a subtraction later and subtract, or maybe I can do it right now. Okay. So, what do I do? You should do it and then make sure I do not make mistakes. So, differentiate this rho times d by dt of du by dx plus use the product rule, differentiating with respect to x, right, du by dx times du by dx plus u d square u by dx squared plus dv by dx du by dy plus v d square u by dx dy, and I am not going to write this because when I subtract it is going to get cancelled off. Okay. and I am going to write mu equals mu times, yeah, yeah, this is y, huh? First one with respect to x. So what am I doing? dv by dx, du by dy, this one. Which term are you looking at? Right side? Oh yeah, yeah. Mu times, 1 second, let me finish. Del square of du by dy. Is this what you are saying? Yeah, I have to differentiate with respect to y. Yeah, thank you. Okay, I thought I had made a mistake only in one term, but I guess I made a mistake in all the terms. Okay, du by dy, sure. No, I was thinking something, there's a problem here. Thank you. So du by, okay, differentiate with respect to y, okay? Du by dy. Du by dx dx dy. Yeah, thank you, man. Otherwise, I was going to be in trouble. Then I have dv by dy, du by dy, v d square u by dy square. Yeah, everything is fine now. Yeah, you got it right. Differentiate with respect to y, and the second one with respect to x. Rho times d by dt of dv by dx plus du by dx dv by dx okay, dy okay. That's what we have. Something is missing again. Which one, man? Left hand side last term, d square u by dy squared. Thank you. Yeah, and this is the reason you people should differentiate, because I forgotten how to differentiate. Subtract. Okay, but before we subtract, I want to do something. Look at this term and this term. I have not written the pressure term, but if you want, you can write it. Anyway, I'm going to subtract, it gets cancelled off. Okay, so I have not written it. Okay, I want you to focus on these two terms: du by dy, du by dx, du by dy, dv by dy. So I can take, so let us take term 1 and term 2. So du by dy, du by dx plus dv by dy, du by dy. What is this equal to? I can factor out du by dy common, okay, and I get du by dx plus dv by dy, and because of continuity that is 0. Okay, so this is 0 because of continuity. So what I am saying is, I don't need to worry about this term and this term. Similarly, I don't need to worry about these two terms, because of continuity they will cancel. Okay, so is that right? Yeah. Okay? Ah, okay. Which one, man? Second equation, left hand side, last term. What's wrong with this? That's correct, no? This one. I am differentiating with respect to x, you are right. What am I doing? D square V by, yeah, absolutely perfect, yeah. Uh, you know, I'm just checking to see if you guys are awake. Okay. Good, good. We are making progress, so subtract, okay. So now I have rho times d by dt of du by dy minus dv by dx plus u multiplied by d square u by dx dy minus d square v by dx squared plus v multiplied by d square u by dy squared minus d square v by dx dy equals mu times del squared of du dy minus dv dx. Okay. Now, what is this? I mean, I defined vorticity earlier. Can you tell me, is this the same as vorticity or is this the negative of vorticity? Is this vorticity or the negative? Whatever I did in the class, man. Just, and capital omega equal to curl of V. Negative, right? So omega is minus of the, I'm just going to accept whatever you people say. Fine. So I'm going to write this as, so I'm going to write the right hand side as minus mu del squared omega. And this will be rho times d by dt of minus omega. Okay? Plus, I write this as, I'm going to right now leave it as it is, but I'll make some changes. So squared, okay, plus v times d square u by dy squared minus d square v by dx dy. Okay. So what have I done? I've just, wherever I've taken this term, put it as omega, minus omega, and I just rewritten these terms and put that as minus omega. That's what I've done. Okay. So now what I want to do is, I want to write this in terms of stream functions, okay. I can write the u in terms of stream functions. The other thing I can do is, I can take d by dx common from these two. I can take d by dx common, so it will be d by dx of du dy minus dv dx, that is minus omega, okay. So what I am saying is, I am just going to labor this point a bit, then you can do whatever you want. So V times, okay, let me do it the right way. I have rho times d by dt of minus omega plus u times, I am factoring out d by dx, and I recognize that this is nothing but du by dy minus dv by dx, and this again is minus omega, okay. And then the other guy plus v, I take out common d by dy and I get du by dy minus dv by dx, okay. And on the right hand side I have minus mu del squared omega, and this again is omega. So my point is, rho times d by dt is omega or minus omega? It is all minus omega. So minus cancels off everywhere, rho times d omega by dt plus u times d by dx of omega plus v d by dy of omega equals minus or plus mu del squared omega, okay. I mean you just have to do it, okay, you will get it. So now the question is, this is an equation for vorticity, and this basically is very similar to your Navier-Stokes equation. Navier-Stokes equation, what did I have? Dou u by dou t plus u du dx plus v du dy equals del square u. So this is like how the vorticity is getting convected in a flow, okay. The other important point which I want to mention is that in addition to this, this is in V, I can write this in terms of stream function, okay. So what is u in terms of stream function? It is d psi by dx, and V is minus, u is d psi by dy, and V is minus d psi by dx, okay. That was the definition for the stream function. And then I have this other thing where I said I related the stream function and the vorticity, remember? I wrote the vorticity in terms of the stream function. Vorticity was del square psi. Was it plus or minus? Plus or minus? Is okay? Okay. So anyway, so basically now I am not have not made any assumptions of rotationality, irrotationality, anything. So this is the conversion of the Navier-Stokes equation in terms of stream function and vorticity, okay. This is the stream function and vorticity formulation which several people use for analyzing two-dimensional flows. Now what I want to emphasize, so basically this equation is a second order equation in stream function, this is a second order equation in omega, okay. And so this is, and what you could do is, if you want to, you can write everything in terms of stream function. You can substitute for omega in terms of del square psi here, okay. And then omega again in terms of del square psi, you can write everything in terms of a del square psi equation, okay. We can, let me call this equation 3 and this equation 4, we can substitute 4 in 3 and get a fourth order equation in psi, okay. You understand? So, wherever omega is there, I will just put psi, del square psi. So, I get some this also in terms of psi, everything will be in terms of psi, and this, now this will become fourth order. So, what this means is, depending upon what you are comfortable in solving, you can write everything in terms of 1/4 order equation in psi, or you can split it up into 2 second order equations, one for psi and one for vorticity, and solve. Different people use different methods, okay. So, this is your stream function vorticity formulation for the general problem. Now, you see what has happened is, for the general problem I have my fourth order equation, which means I can now, I have not made the assumption of irrotationality, I can satisfy all the boundary conditions. Remember, you had 4 boundary conditions. So, now the boundary conditions which have to be satisfied are, again, let us say 2 walls, okay, u equal to 0, v equal to 0, u equal to 0, v equal to 0, no slip, no penetration. You have to convert this into stream functions, because now I have to convert the boundary conditions of no slip and no penetration into corresponding stream function variable, okay. So, u is nothing but d psi by dy equal to 0, and v is d psi by dx equal to 0. So, I have d psi, this at this wall, d psi by dy equal to 0 and d psi by dx equal to 0 as an example. The point I am trying to make here is, now I have actually I am satisfying both the no slip and the no penetration boundary condition, because now this equation is going to be fourth order in psi, yeah, when I substitute for omega in terms of psi, okay. So, there is no singularity, no business of letting go of one of the boundary conditions. So, here I am solving the full problem, okay. So, here in the general problem, all the boundary conditions can be satisfied when the flow is rotational, okay. The other important point is this term here on the left, this term here is the one which is giving rise to my non-linearity, okay, because I have some psi multiplied by some psi. Remember, when you have products of psi, this becomes non-linear. So, these are the inertial terms. These inertial terms in the Navier-Stokes equation are the ones which create the problem, which makes it difficult to solve, because after the math course last semester, you are all experts in solving linear equations, right. So, this is the one which makes it difficult, and in the limit of very low Reynolds numbers, the creeping flow limit, what people do is, you can put these inertial terms to 0, and we will do that next class to see the conditions under which it goes to 0. So, supposing you can neglect these inertial terms, the terms on the left hand side, then what do you have? Del square omega equal to 0, omega is nothing but del square psi, so you get del power 4 psi equal to 0, okay. So, in the creeping flow limit, inertial terms on the left can be neglected basically Reynolds number tends to 0, okay, we will see that, and you get del square omega equal to 0 and omega is del square psi, and therefore del power 4 psi equal to 0. And this is a homogeneous equation which you can solve by separation of variables and things like that to get a solution. So, now you can see that in the limit of low Reynolds numbers, okay, when I am doing this stream function vorticity formulation, I get a linear equation which I can hopefully solve analytically subject to boundary conditions. So, that is an advantage, okay. Thank you.